Okay, so here we are at day 7. Yeah. Okay. um, now, um, as far as questions goes, so you had one right away.
Yes.
Yeah.
So
About the homework. Yeah.
when we do in the exact solution where we set that up and we just talked about in your office of doing the array.
Yeah.
For some reason, I get a message that says something about this can be executed with a float. It's like it's treated as a integer or something.
Oh. Let's see. Oh.
It says float object cannot be interpreted as an integer.
Oh, that's okay. That's strange. So, because in your solution code, it's important to because what's happening is like by default, the initial conditions, if you just type them as simply as possible, are going to be integers. They're converted to floats. But I'm trying to think of why I would try to interpret something as an int. But can you pinpoint like what line it's complaining about?
That specific line where we do the np.nd array and then we do the math to put both of those solutions in there.
Okay.
And that's the error we were getting the other day, and so that's why I separated it like I just showed you in the office, and then I didn't get the error anymore.
Okay.
Also, it won't run when I took these indexes out, and then I had zeros and one here. When I took those out, now it just takes.
Those are possible. Well, obviously we can floats, but. Okay. Oh, okay. Oh. Uh, oh. Okay, so that looks right. So.
Because I don't even know what it's trying to interpret.
Yeah. Yeah. And, okay, so let's call this. Um, um, sub 0. So that way it's picking up one element of it. Yeah. Yeah. Okay, so it's not good for building the list. Just want to make sure of that. Now, okay. Now, I'm going to try to reproduce exactly what you were doing here at the console. Okay, so the serious error that was happening is so T is a okay. Well, I'll import what I need. T was a list of oh, whoops. Okay, so these are the same numbers that you had, except for possibly a little round-off error. And what you were doing just now was np array, and oh wait, I need to import math. Okay. Duh. Okay. All right. So, and you're doing math exp minus t first element squared. And it took it. So that's extremely odd.
Does it have to do with the 4T and T part?
No, that's why I had you separate it out. So the line above it is where it's complaining now. Let's okay. The original line you were having trouble with. So is Haley having the same problem?
Mm-hmm. We tried to do it the other day. That's why we had to separate.
Okay. Okay. So now we have. Oh wait, I still need this to be an array. Oh. Oh. Whoops! I wiped out my list. Okay. Oh. Oh. Sorry, I goofed. I have to make these lowercase t now. Okay, this is because that is it's the same line. Okay. I have a hunch, maybe. Let's think what can be done differently. And that is, well, that shouldn't matter. But okay, so I need to do that. Oh, that's array is okay. I also has to do. So I was like, try having a line here in your main code that only does call the exact solution and it saves it in the array. something I normally would not like to do, but, well, since this is not the main part of the code, I can open this part of my solution. Okay, so I just do a return. I don't see why that would make a difference. But as you can see, it's exactly the same. And can you give me read off the error message so I can type it in exactly?
Float objects cannot be interpreted as an integer.
Okay. I was curious as to how was this encountered. $60. Like in this sample code here, if the user types in an integer, it's read as an integer, but then it is divided. Okay, but that's for like ranges, for instance, but that's not really applying here. Okay. Oh, that's for something else, unrelated. So, yeah, it's like at what point would it need it to be an integer? If it's, and also, this might be interesting to try. Now, in your exact solution, so what would be interesting to do is actually, if I do type of T, oh, it just says list. So T is coming in. Okay, do this. I assume these things can be printed. Yeah. Oh, yeah. So if you go ahead and print out the type of capital T, which I believe should be a list, and also print out the type of capital T of 0. Now, by all appearances, it's a float. But I feel like something had to be the wrong type at some point. Yep. Okay, that's extra weird because when you printed it out, it was 0.1. Okay. Now, because you were printing out T earlier.
Okay, now when I print it out for not 0 but for 1, then it says float. So I guess it's treated the first one, which is 0. I guess it's treated this as an int.
Ah, the first time value. Okay. Now, if okay.
When you print your first T, your T not what is yours?
Let's find out. Okay, and this will solve the second one. Okay. Okay. Oh, first time value is an int.
But you're not getting an error message though.
Yeah. Now, and then the second one from that point on is a float. Yeah. Okay. Now, so yeah, okay. So it's a list of all floats except for one int. Okay. Float cannot be interpreted as integer.
Haley type is that same thing that you have there and that I have, and she got the same error.
Yeah. So. All right. So here's the same situation. Int followed by obvious float. So. Okay, here's something I'd be interested to try. Do this at the prompt. So, oh, okay. Yeah, like this to create the same T. Although what's kind of weird is, oh, okay, this makes the first one a float, but what you can always do after that to make it the same is force it to be an int. And then every other one after that will be a float. So create the same, well, presumably the same capital T in the console, and then just do this, exact solution to T at the prompt, and see what happens, see if you get the same error. Yeah.
Same thing.
You get the same error? Okay. All right. I hate taking this kind of step, but make sure you're at the prompt, not an editor window. Like click in the console window, and do since you're on a Mac, Command W, and what that will do is close the console and open up a new one. And actually, I can do the same thing. Now, certain things will have to be re-imported. So you'd be importing your own ODE test and importing NumPy, and then recreating that. Oh, if you just import that, actually, I think. Oh, whoops. Oh, this is what you would type. I would append this. Okay.
No, it says T is not defined.
Oh, did you do this up here? Yeah.
Same error. Okay.
What on earth?
I have exactly what you have typed there.
Yeah.
Create T, and then return emp.array
Um,
Yeah, I don't know.
The only, I don't know if there's some sort of version difference. But again, like Haley's on Windows, right? And you're now on a Mac, so. Um,
But then I don't get that error when I separated it like I had showed you before.
right.
But that's not right.
Yeah. Actually, go ahead and send me both your files,
Okay.
and I'll see if I'm able to reproduce the error. Just to try to narrow things down a bit. Ugh. I hate mysteries like that. I don't suppose anyone else is um, uh, having a similar issue.
Well, I did in my code,
Okay.
but it wasn't in the function itself. It was in, I had created a relative error and absolute error functions.
Yeah.
That had spit something back out, of course, calculating in a simple way, produced a list. I simply corrected that problem by calling a function that would extract, a list with a single element, so I simply used the max function because
Okay.
that's a cheesy way of solving a problem, but
Yeah.
it was a cheesy function to begin with, so
So
it was saving me a few
so
few seconds.
two cheeses make a.
Two cheeses make a really nice sandwich. But anyway,
Okay.
it might be some. It did say reading float as int when it wasn't that problem. For me, when it was simply a problem of reading a single element list.
Yeah. Okay. So.
I sent it.
Yeah. Okay. Okay, so now if I change here to, okay. All right, I'm going to close this console and open a new one. Okay, so now I'm in your directory. And if I open up this, okay, and run it.
Okay, now that's that other error where it won't run. You might have to go to the solve one and come in out there.
Okay. Another strange thing to deal with. Okay, so actually, right. Well, okay. So I won't do this. I'll just create T. All right, and I'm going to comment all this other stuff out. Oh, at least we're getting the same error. Okay, so all right, that's the correct T that's coming in. All right, list float. Okay. Oh. I know why. This is a whole kick yourself moment. Here, take a look at this line, and now my line. Here, there's a difference. Okay, so actually, if you have
Oh, it's not in the array.
right. Okay, ND array is a function used to create an array of whatever size and however many dimensions. And the first arguments to ND array are the dimensions, which are integers. You gave it some floats, so if you do array, not ND array, then it should work.
So that problem was still not run when I do that.
Okay, so that's a separate thing. Well, now I have your code, so I can look at it later.
Alright.
Okay.
I think that's what happened. We both were using the ND array. That was
Yeah, and you can. It's just careful how you call it. Yeah. Well, let's pull that up anyway. I'll need to make this bigger. Okay, not that big. Okay. Oh, actually, I don't want a reference. Oh, this is going to take forever doing it that way. Well, okay, so it's a class, but therefore has a constructor. Yeah, shape is the first argument. Yeah.
so we was taking that in as the shape.
Yeah. Yeah, it's like, why would it need to convert a float to an int?
I know.
And now we know.
Makes sense.
Yep. Okay. Yeah, the thing is, I was looking at your code, I was like, I don't see anything wrong here. And at some point, it took me a while to notice it. And yeah. Okay. Yep. And this is how it always goes. Whatever it is, you're like, dang it. Okay. Does anyone else have any pressing questions about the assignment? Okay.
What's the next one?
Okay. Well, that is the next thing I'm going to do. Anyway. Okay. So, all right. So I'll close this. Close this. All right. So, okay. So, so the assignment, homework 2, will consist of 3 files. I guess no one of them is really considered the main, or I guess there are 2 main programs. Okay, so I'll just type the assignment description in this one, since it's likely the first one to work on anyway. Whoops. Okay. Oh, because I typed in a colon, it thinks I want to indent. Like, no. Okay. All right, and I say maybe, depending on how much difficulty, for remaining difficulties with the first one. And, well, actually, all of you have been in a class with me before, so you know how I feel about deadlines. Okay, and actually, I'm not even sure what the third assignment will be anyway, so I want to give myself time to think about that. Okay. Okay. So, so this is all about AX equals B. So the method that I will show you is, and that's today, Gauss elimination without pivoting. What you will do, Gauss elimination with pivoting, forward and back substitution. And then a main function like solving A equals B. Well, those of you who took 561 with me last semester, which 4 of 5 of you in this room did, you wrote a MATLAB solve AX equals B function, and now you'll do it in Python. They'll be similarly short. Okay, but then I have more. Iterative methods. Jacobi, and 2 versions of it. Not direct. Full and sparse. So in other words, and then the same thing for Gauss-Seidel. Okay. You know what? I just realized that I meant to include SOR and I forgot. That's okay. But once you do the other 2, it's not really all that interesting. And one more. Conjugate gradient. And that's actually meant to work with either one. So what's interesting is what you'll see in my discussion, because I'll have an outline of most of these functions, that for full and sparse, while it's rather difficult to implement versions of Jacobi and Gauss-Seidel, like one version that will work whether you pass it an array or a or SciPy sparse matrix. You can, but you're going to need like if statements and so forth. Now, conjugate gradient is generally intended for sparse systems, large sparse matrices. But the only thing it really does with a matrix is matrix vector multiplication, which can be done the same way with a full or a sparse matrix. So it doesn't really have to care. Whereas in stationary iterative methods like Jacobi and Gauss-Seidel, and I'll talk about these in a little bit, because some people in the class may not have seen these in quite some time. You have to solve a system, like a diagonal system for Jacobi and a lower triangular system for Gauss-Seidel, and the way that is done is differs for whether your object that's passed in for A, your matrix A, is a like a NumPy ND array or a SciPy sparse matrix. You're calling different functions for those situations. So that's why I thought, well, let's just punt and have you guys implement 2 versions, one for full and one for sparse. Okay, and then there's some testing code which I've supplied that will use conjugate gradient. Like I'm making small systems up for this, very small systems. And for conjugate gradient, making a somewhat larger system that's meant to solve a 2-point boundary value problem, like I demonstrated in class. Okay, so all right. So there's 3 files. There's this one, Gauss Elimination Partial Pivoting, where you'll do items 1, 2, and 3. And then there's another file, iterative, which we'll talk about later, where everything else will go. But then there's one other thing for testing purposes, function called read matrix. And so a file I'm putting out there, mat utils, like matrix utilities. It only now for assignment, there's only one function in it, read matrix. But I give it the file a generic name because, like, what if we want to put other things in there for doing generic operations on matrices? Okay, so I think what I'll do is I will talk about this function first, because it doesn't really get into any of the algorithms, and we'll break at that point. Okay, so the idea here is the purpose of this function that you're going to implement is to allow the user to type in a matrix at the prompt, entry by entry, in a somewhat user-friendly way. So what I'm going to do here is, okay. Okay. So I'm going to import, oh, whoops. I have to do my solution. Oh, wait, wrong file. matutils solution import read matrix. What? I'm still in the Brianna directory. Whoops. Okay. All right, let's try this again. Okay, now I have it. All right, so now what I'm going to do is I'm going to do a equals read matrix. I'll demonstrate what the output should look like, so then you can see this when I post it later. Okay. All right, so prompts user for how many rows are in the matrix. I probably could have made the prompt a little clearer, like enter number of rows, but you get the idea. So if I'm going to enter a 3 by 3 matrix, and so now that it knows how many rows you want, it's going to prompt me for each of those rows. So, and this user interface is flexible, because you know how in MATLAB, when you're typing in a matrix entry by entry, each row you can have the number separated by commas or by spaces, whereas Python it has to be commas. So for instance, for first row, I'm going to do 1, 2, 3. And then here I'll separate by spaces, and it accepts it. And then what I'll do is I'm going to type in too few numbers, like only 7 and 8. And so it'll accept it, and it tells me that because I didn't type in enough numbers, that the last one, it assumes that I wanted 0 for that. So now if I display A, sure enough, it fills in that last entry being 0. Also, if I had entered too many numbers on a line, it'll tell me that those extra ones are going to be ignored. So it tries to be somewhat idiot-proof anyway, but not entirely. Like, for example, if I run it again, okay. Well, actually, let's see what happens in this case. Yeah. Here I give it something and it simply cannot understand as a number. Because it's going to try to convert whatever you type from text string to floating point. And if it can't do it, I didn't set up my code to handle that case out of laziness. But if you really want to go above and beyond and research exception handling, you're welcome to do so. It's something I'd like to cover later. Okay, so that's how a function is supposed to behave. So here I have an outline, or a framework for you implementing that. So here's a specification of how it's supposed to behave. So read a matrix of whatever size specified, accepting comma separated or space separated lists, and then how it handles too many or too few entries. Okay, I don't like it highlighting entries. Stop that. Okay, all right. So, okay, so like you saw in the output, prompt a user for the size that they want, and then allocate a 0 matrix of the correct size. Make sure that it's a float. So you can use the zeros function from NumPy to do this. You're allowed to specify a type. Now, so one thing to keep in mind is here I have referring to various Python functions, most of which you've seen, some you have not. So if there's an expectation improvement assignment and you come across an unfamiliar function, you should look it up in the documentation. And so if it's something from NumPy or SciPy, on the site, under Resources, I have this link here to the to SciPy, and to go to the site, it's just scipy.org, and from there, okay. So under SciPy, here you can go directly to the documentation for all of these. Let me make this a little bigger. Okay, and then you can get to the documentation for NumPy and separately for SciPy. So I will indicate what packages any such functions are in. So that'll help you find them. But if you go here to index, so this has a function of the index of every single function in SciPy. So you can look up things there. Now, certain functions are more generic. We'll come across those. But most things we need are in NumPy or SciPy. In preparing this class, I find myself looking these things up all the time to learn about certain nuances and so forth. So it's important that you do the same. Or if it's something that's not part of NumPy or SciPy, just like Python language itself, I'm Googling constantly. So in fact, I literally Google Python and then whatever I'm asking about. Like how to do this or what is this function. And I find myself on Stack Overflow a lot. So you guys should get in the habit of doing the same. Okay, so let's get to be looking at the zeros function. See how I can make sure that when you allocate a matrix of a given size, that the entries are considered floats. Okay, then you'll handle each row. So you'll have a loop that'll prompt user for each row. So here, you're having it. You're telling which row to enter, because notice in my case it said enter row 1, row 2, row 3. So whatever index you have for your loop, you got to add 1 to it, because remember Python uses zero-based indexing, as I seem to say several times a day. One comment I made further down, but I should really do it up here. Use str to convert numbers to text strings. So when you're building this string, and remember, you can literally add strings together. So you can have like, so as an example, I can do something like this, plus str3, and it'll create the string that way. So that's how you can build up strings involving numeric variables and rely on this to convert it to a string for you. And the plus is for concatenation. So what happens is you're using the input function to get whatever text the user typed as a text string. Now, you can use the len function. Len is for length, to give you the number of characters they typed in. So what if they didn't type in anything? Like, I'll go ahead and call my function again. All right, so I'll put in, if I type in nothing, then it's okay. I have my code, have your code check for that. So if the length of what they typed in is positive, then you know you have something. Otherwise, down here, if they didn't give any entries, and you tell them that those entries will be assumed to be 0. So if I look at my matrix A, sure enough, the second row is all zeros because I didn't type anything. It might be a good idea to get a nice case to work first, like the user types in actual numbers. for every single entry. They don't type in any extra. If it's a correct number of entries. Get that case where a user does the right thing first. Get that working, and then you can go back and handle the exceptional cases. Okay, so if they entered something, well, you don't know if it was separated by commas or by spaces. Now, there's a nice function, so you have a string dot split, and you give it a character. And now what that does is, it's really nice for parsing text. If you have a list of something that's separated by like a comma or space, what you can do is, like, here's an example. Here's a string that has 3, 4, 5, and I call that S. So I do S dot split, and I specify a comma as the argument. So that's saying, give me a list of substrings obtained by looking for commas and breaking a string up where the commas are. And now what that does is, in this case, it gives me a list of strings, 3, 4, 5. So if they are separated by commas, split will do the job for you. Now, what if the user didn't use commas, they used spaces? Well, that's easy to check, because if it didn't find a character, it'll just return the whole string back. There was nothing to split. So then, so in other words, if they didn't use commas, then there'd only be one item in the list. The length of this list is 1. So you can check that down here. So if the length of a list returned by split is 1, there were no commas. So try splitting again, but instead of a comma, use a space. So that way you can handle either one. So you just try one and then the other. Okay. So now at this point, you've done the splitting. You have however many entries the user typed in. So now you check. Did they type in not enough entries, too many entries, or the right number of entries? And you handle each case accordingly. So if it's too small, then you just take whatever they did type in, store it in the matrix, and then now you already allocated a 0 matrix, so you just store whatever entries they typed in. The rest are already 0, but you have to tell the user this, that these entries are assumed to be 0. Okay. And you don't have to convert. The numbers are still text strings. That's what split gives you. But you can actually assign those to a matrix, because that assignment will implicitly convert the strings to floating point numbers. So it still works. Okay, so I explained that here. If there are too many entries, well, there's an n by n matrix. So you take the first n entries, store them in that row, but also give a user a message, and I'm indicating here what the messages should be, so that when I run your code, I can have it behave the same way as mine. If it typed in the right number of entries, that's the easy case. You don't have to print out any message, so you just store them in that row. And then this is a case where if it didn't type anything, you don't do anything to the matrix, but again, you tell them that these entries are assumed 0. And then that matrix that you get, now that it's filled in, just go ahead and return it. So that's the framework for reading a matrix. So then once you have this, then in testing your other functions, you can type in a matrix. That might be rather cumbersome after a while, but and there's certainly many other ways to create a matrix. But you have a question?
No.
Okay. Does anyone have a question on read matrix? All right. Okay, we'll take our first break and see if we can figure out the other mysteries in your code. Okay, and then we'll talk. Okay, we're back. Yeah, that was an unexpectedly long break. I tried to think of various things that happened with your code, any lessons for the class in general. The main thing I can think of is that aside from a very limited situation where you're making copies, you're setting up your initial data y0 can come in either as a number or a list, depending on whether you're solving a single ODE or a system of ODEs. And so in that case, you have to check, like, is it a scalar to set up your y0 to, like, your first y value to get going. Other than that situation, the code should pretty much work not caring whether it's a scalar matrix. The only other situation I could think of is when you're doing the error estimates. In that case, too, you're taking absolute value if it's a single ODE, or a vector norm, infinity norm, if it's a system of ODEs to get your error estimate. But the actual formulas, like for the Bogacki-Champine method, shown here, to basically be you just code it up the same way, and whether your y's coming in happen to be an array or a number, because your f, whatever your f is going to be set up properly according to whatever kind of problem it is. So the way you implement these, it's like you get it working for one and have it automatically work for the other without having to make any changes to that. Okay, but a lot of the more vexing errors come about from, like, overwriting something that you don't want to overwrite. That's a very common one, because then you think it has some value, and then it turns out to have something totally different that throws it off. Okay, now I need to continue describing the second assignment, and then we'll have time at the end, presumably, for the any discussion of the first one. Now, somewhere here. Okay, so I've talked about read matrix. Okay, so what I'm going to do here, and these files for the second assignment will be posted on the assignments page later today, is I'm going to show you Gauss elimination without pivoting, and then talk about the other direct methods. So here I have GENP, Gauss elimination, no pivoting, taking in a matrix A. Now, so if I get the shape, okay, and I'll try using this function. Okay, so that gives me a tuple list of parentheses m comma n, where m and n are the size of a matrix. First I want to do some idiot proofing here. If the length of this needs to be 2, but it needs to be a number of rows and number of columns. So if it is not 2, then I'm going to raise heck an exception. That it needs to pass through something that can be recognized as a matrix, something that's two-dimensional. So not dealing with this code doesn't have to work with tensors. I know. Okay, so now that I know that it's 2 elements, I can do this. M comma n equals the shape. So basically, this splits out the 2 elements of size as z, and stores first one in m, second one in n. So now that I know I have a matrix, I need to make sure that's a square matrix. So if these dimensions are not equal, I'm going to raise a different exception. Yes, and then I have a tendency to yell at my users by putting exclamation point to my error messages. Okay. Now, what I'm going to do is, Gauss elimination produces upper triangular matrix U, the row echelon form, and then the multipliers can be stored in unit lower triangular matrix L. So I'd like to just, so reducing A to U, so what I'm going to do is I want to make a copy of A in U. So I'm going to say U equals A dot copy, and remember you have to copy Otherwise, A will be modified. I don't want to modify A. So if I just said U equals A, I'd reduce it to the upper triangular form, and then A would be overwritten with that form as well. But I only want that in U. A needs to be preserved. Okay, now I can actually begin the Gauss elimination algorithm.
Dr. Members?
Yeah.
I think if you have if len z, isn't that supposed to be SZ?
Yep. Dang it. That's what I get for not following my notes.
You're still in the Brianna flow too, I think.
Oh, yeah. Oh, for that, I can do CD dot dot to go back. And earlier I did that to change it. So you can do CD within the console. I don't know if it'll work in your scripts, but certainly from console you can do that.
We should try that.
Yeah, that's a point. Okay, so now I need to go through all the columns. Now I don't need to go through all the columns, just up to the second to last one. So I could do range n-1, and that will be enough. So I eliminate subdiagonal entries in each in column J. So for that, I will loop over rows starting from J plus 1 all the way to the bottom. And now I get my multiplier. So Mij is Uij over Ujj. Actually, I'm going to put the algorithm up in pseudocode, so you have that to look at. Where'd it go? Here it is. So yeah, this is what I'm implementing right here. I'm just doing all the work on U. Okay, and then so then to actually perform the row operation. Well, first I'm going to store this in the lower triangular part of U, which will actually become L, the LU decomposition. Okay. Now notice, I is always strictly greater than J. The Ij entry, when I is greater than J, is in the strictly lower triangular part. So for any Ij, that's where it's going to go. So in other words, it doesn't overlap with the upper triangular part where we store the row echelon form. Okay, so this is find multiple of row J to subtract from row I. So that's what the purpose of a multiplier is. Okay, and then so row I equals row I minus Mij times row J for elimination. So I do for K in range, and I'm going to go from J plus 1 to N. So that's the only part of a row that contributes to the row echelon form. So I'll do Uik. So in other words, element K of these rows is what I work on in this loop, equals itself minus, so I do this minus equals. So this equals itself minus multiplier times Ujk. All right, so that performs the row operation. So this is enough to reduce A to an upper triangular form, but now what we have is the upper triangle of U has the row echelon form. And actually, I'm going to comment here. It's what this is producing. So the output is unit lower triangular matrix of multipliers. And U is upper triangular matrix. It's a row echelon, using a free 26 lingo, form of a results from Gauss Elimination. Okay. So, all right. So to recap, loop over all the columns except the last. Oops, I forgot the in here. I saw it squawking over here, so that's how I knew that something was wrong. Then for each entry below the diagonal in that column, we're going to eliminate. So we find the multiple we need, store it in the lower triangular part, then we perform a row operation on the rest of this row. In other words, from one entry to the right of the diagonal onward. One entry to the right of a column that we're in, all the way to the end. So that's why we do from j plus 1 all the way to n. Okay, so this carries out the elimination, but now we have a matter of storage, because I don't want these multipliers staying in U. I want them in a separate matrix L. So what I'll do is, now L is unit lower triangular. And it's a lower triangular matrix where all the diagonal entries are equal to 1. So I will start by creating an n by n identity matrix for L. So this ensures diagonal entries are all 1s. And now what I'll do is I'm going to loop through the lower triangular part of U. So I go through all the rows, and then for each row, I loop over all the indices j that are strictly less than I. So in other words, this ensures that j is strictly less than I. So in other words, the ij entries we're examining are all in the lower strictly lower triangular part, the subdiagonal part. So now I will copy each multiplier from U to L, and I don't want it to stay in U. So I'm just going to set it equal to 0 in U. And now my LU decomposition is complete. So I can just return L and U, and I'm done. Okay, so that's the entire Gauss elimination, LU decomposition function for the case of no pivoting. And I'll make the note here that this is implementing algorithm 3.1.6 essentially to do at least to do the elimination part. The storage is not featured in the algorithm because in the book LU decomposition isn't covered until later. But it's saving the multipliers that are needed to do overall operations in the lower triangle. Okay. All right. So any questions about this implementation? Okay. Now, the row operation mathematically applies to the entire row, of course, and all entries to the left of column J are already 0, so we don't have to think about those. We don't bother with Uij in this loop because within U we know what's going to be. It's going to be 0 anyway because it's a subdiagonal entry. And second, Uij is needed to store the multipliers. So that's why we don't include this in this loop. Okay. So, all right. So now, if you haven't, so like those of you who did not take 561 last semester, you haven't touched numerical linear algebra in a while, what I would recommend is going through, so section 3.1 reviews Gauss elimination. It does it for some simple examples. Okay, so chapter 3 in the text is all about AX equal B. There's a linear algebra appendix also at the end of a book that has linear algebra fundamentals. But it covers simple cases like triangular systems, like diagonal, upper triangular, lower triangular, that you would solve using either division or substitution. And then does some examples of Gauss elimination and back substitution. Here's a back substitution algorithm. And then handling row operations to reduce a general matrix to upper triangular form. So this is what you learned like in your first linear algebra class. And then now after stepping through an example or two, then developing the entire algorithm that you see here. Okay, so we got a good idea to have an understanding of how that algorithm works, because this decomposition does not always exist for any invertible matrix, because for situations where you might have to interchange rows. Like, what if a 1-1 entry is 0? What I just implemented would not work for that case. Now, the LU decomposition is discussed in the text in 3.2, in case you want that review. And so it's how from Gauss elimination you end up with the LU decomposition using unit lower triangular matrices and so forth. And then how do you solve AX equals B? So this is what the code is meant to do. You carry out the LU decomposition using Gauss elimination. So you're basically performing this factorization. That's what I just wrote. Then use L to solve this system Ly equals B, where X equals B is the system you're originally trying to solve. Then that Y, the result of that, Y is the right side of this system, Ux equals Y. So this is lower triangular, so you use forward substitution. Ux equals Y, you use back substitution because U is upper triangular. So this portion of the book discusses the whole solution process for AX equals B. And then further down, there's a discussion of pivoting. Okay. All right. Now, okay, so what the first thing for you to implement besides read matrix, first thing to implement for you to implement this file, Gauss elimination PP, partial pivoting. And so in the book, section 3251 discusses partial pivoting. So what you're doing is you look at the column that you're working on and you scan the column from the diagonal to the bottom. So row J down to row N. And you look for the largest element. And once you find the largest element, assuming it's in row P, then you swap row P and row J. So that's what's discussed in here. And so as long as the matrix is invertible, this is guaranteed to work, that you can carry out the Gauss elimination process. So partial pivoting is explained in here. So what will happen is, now for most part, you're going to use the code that I just typed for Gauss elimination without pivoting. You just have to change the pivoting part. So up in here, before you before this I loop, so within each column, so between here and here, between these two lines, that's where you'll handle pivoting. That's where you'll find out if you need to interchange rows, and if so, go ahead and carry that out. Okay. Now, Gauss elimination with pivoting returns a slightly different factorization. I'll scroll to that. So it's PA equals LU. So P is a permutation matrix that carries out over row swaps. So if a row swapped version of A is what gets factored into L and U, and then you solve a system of equations, Ly equals PB, not B, and then Ux equals Y. So step 1, Gauss elimination and pivoting. Step 2, solve this using forward substitution, and then solve this using back substitution. Okay. So a permutation matrix is could be when you're starting with identity matrix, and then you're swapping, you're rearranging its rows. So it's a matrix that has mostly 0 entries, except for in an n by n matrix, there are n entries that are equal to 1. It's wasteful to store that as a 2D array, so we're not going to here. We're going to represent the permutation matrix as a vector of indices, so 0 to n minus 1. And so whenever a row swap is performed, the corresponding indices of P are also swapped. So then that gives you an idea as to how the rows were scrambled during the entire process. So initially, P will be all the indices in order. So I suggest using a range to create P. That way you can change the entries of P as you go. A range is from NumPy. And I demonstrated that in the tutorial. So when you're looking through an array and finding the largest element, in this case, we don't care what the largest element actually is. We only care where it is, what index it is. So for that, instead of using max, use argmax. So here's a simple example. I create an array, and the largest element we can see is the 5th one. So I do x dot argmax, and 0 indicates I want the very largest element. Like if I wanted to, I could use this to find the 2nd or 3rd largest by passing like 1 or 2. But here it passed 0, indicating I want to find the index of a maximum element. And it would return 4, because remember it's 0-based indexing, so that's the index of the 5th element. So I can use argmax to tell me the index of the row that I want to swap with. Now keep in mind, I'll put a comment here. Checking rows j through n of column j will give an index between j minus 1 and n minus 1 because of the 0-based indexing. Well, actually, no, it won't. 0 and n minus 1 minus, okay, 0 and n minus j. But that row has an index between j minus 1 and n minus 1. So the index returned by argmax has to be corrected, has to be shifted, so that when you're referring to that row of an entire matrix, the n by n matrix, it'll be the correct one. So keep that in mind. Now, once you know what row you're going to swap with row j, if you need to, because when you find out, okay, here I'm looking for the index p that satisfies this. If p is equal to j, there's no need to swap. But if they're not equal, you do need to swap. Now, how you swap rows of a matrix, I actually did this in a June 7 tutorial. So if you go to the site, under June 7th, and this script, tutorial 0607.py, it's in there. So I carried out that same task, so you can do it that same way. Whereas in P, the vector, the one-dimensional array P, to swap two elements of it, that's easier. You can just do this. So basically you do AB equals BA, and that swaps A and B. So that works quite well when the items you're swapping are scalars. I tried it with entire rows of matrices and didn't like that. So that's, but you can see what I did in the tutorial. Yes?
About argument max,
Yeah.
shouldn't it be absolute value?
Well, yeah. Whatever you feed here, take the absolute value beforehand. Yeah. But yeah, you do need to remember to do that. Okay. Yeah, because of this. Okay. Okay. So then, other than this, the Gauss elimination process will proceed as I showed you in a no pivoting case. It'll just return free output, L, U, and P, in that order. Okay, so that's actually the hardest function in this file. Here you're implementing forward and back substitution using the algorithms that are given in the text in pseudocode. So once you've done Gauss elimination, these will not be very challenging. And then an overarching function to put it all together. So you take A, you pass it to your Gauss elimination partial pivoting function to get L, U, and P. And then after that, you use your forward substitution and back substitution functions to solve the systems that I described here. Oh, wait, I went too far. Yeah. So you solve Ly equals PB and Ux equals Y. Now for solving Ly equals PB, P times B is the vector B with its elements rearranged according to how the rows of P are rearranged. But you don't have a permutation matrix P. In this case, you cannot do P times B and get what you want because P in the code is not a permutation matrix. You can't do this matrix vector multiplication. It's a vector of indices. Fortunately, it's very easy to do. Okay. So I did this in the tutorial. You can use the take function, which I used in the same tutorial file as for swapping rows. So you want to look at that for two reasons. In order to, because the take function is used to take certain indices of an array. So what you can do, you can use a take function to take the elements of B in the order of the indices specified in P. So that's how you handle the PB part. And once you have that scrambled vector, that's what you pass to forward substitution to solve system Ly equals PB. And then the result of that gets passed to back sub to solve Ux equals Y. Okay. I have a main section here that you need to fill in. So create your own matrix, A and vector B, for testing purposes. And you can use this function, scipy.linalg.solve, with your A and B. Use scipy to compute the solution. So that's like the equivalent of in MATLAB using backslash. So you can compare your computed solution against what scipy computes and make sure they match. Okay. So any questions about the direct method part of this? For the other file, iterative methods. Okay. All right, so I have 5 functions in here. So Jacobi for a ND array, Gauss-Seidel. Once you do Jacobi, Gauss-Seidel will be very similar. And then sparse version of Jacobi, sparse version of Gauss-Seidel. There'll be some differences there to working with sparse matrix. Then conjugate gradient for whatever matrix you give it. And then here, in this case, I've supplied the testing code for you. So I create a 3x3 system, and I use that with all the stationary methods, Jacobi, Gauss-Seidel, and then I pick a tolerance and maximum number of iterations, print out the solutions, which should these solutions will not they won't necessarily match. They'll be very close to one another. And then, however, this solution ought to match this one because it's the Jacobi method, just working on a different representation of a matrix. And these two Gauss-Seidel should match. So what I do is I take my regular matrix A as an ND array, and I convert it to a sparse matrix. I have to pick a format. So, so this is from scipy.sparse, that's SP. Like you have my my imports are all up here, so those are given to you. Okay, so so I convert to coordinate format. It doesn't really matter. I'm just testing this out, but and the thing is, this will work with these functions need to work with whatever kind of sparse matrix is given. So now for a separate example, I create a matrix that is symmetric, positive, definite. Oh, you know what? I need to comment this out because I'm not actually using it. Or actually, I'm just going to delete that. This is what I'm using. So I create a 100 by 100 matrix that is the second derivative matrix. So -2 is in the diagonal, 1's above and below. And here I'm using a broadcasting of scalars like I talked about earlier in a previous class to create the matrix more conveniently. Then I set up a 2-point boundary value problem using finite differences. And this is a problem I'm solving. U double prime equals x times 1 minus x. This is the exact solution. It's 0 on the boundary. Those are my boundary conditions, for at least to this exact solution. So now I create this right-hand side, x times 1 minus x, and I multiply by my delta x squared on the right side. So I can either divide my matrix by delta x squared or multiply the right side by delta x squared, and I chose the latter. Like I did this last time. And then I call my conjugate gradient function and have it print out the solution. And then you can try computing the exact solution and comparing. Yeah. Now, what's interesting to try is if you try this with 2 different values of n, do you get order delta x squared accuracy? Like if I cause dx to be reduced by a factor of 2, the error should be reduced roughly by a factor of 4. But that's due to the discretization error of finite differences. I'm also not solving ax equals b exactly. I'm just solving it approximately. But is the error still second order accurate? So that's one question that I want you to investigate after you get all this working. Okay. Now, to discuss the iterative methods. Okay, so I have a framework for Jacobi. The first part of this is similar to what I showed you in Gauss Elimination. Like make sure it's a square matrix. Now, the parameters are A and B, and an optional initial guess. Now, you do it to pass something. You can either pass a vector, like a list or an empty array, or if you pass an empty list, then it's assumed that you want the initial guess to be the 0 vector. And then I have a tolerance optional. The default tolerance is 10 to the minus 6, and you also can specify the maximum number of iterations. But if you don't specify it, the default is 200. So these last 2 arguments, you don't have to pass them at all. If you don't, then these values indicated here will be filled in. So that's pretty convenient. Okay. So if the user passed just empty square brackets, like that's what I did down here for your third argument, then I just set the initial guess to be the 0 vector of the appropriate length. And then I set x, which is x is referring to the current iterate, so initially it'll be x naught. But again, make sure it's an array of floating point numbers, no matter what the user passed in. The user might have passed in a list of integers. Make sure it's floating point. Just save some headaches later. Okay. Similar to how it's done in the first assignment. All right, you're keeping track of a number of iterations, because that's one of the outputs. The outputs are the x that you compute, how many iterations took place, and then a flag. That's just a number. So 0 if it succeeded, 1 if it didn't. So converged or not converged. So you set your iteration count to 0. And then, in a loop, you carry out all the iterations up to whatever the maximum is. So you can actually use a for loop. So the equation in the text is in chapter 5. Okay. Equation 5.2. So this is your formula for the Jacobi method. So the elements of the new x are determined in terms of the entries of the old x. Now you don't have to store all the x's. So this index k plus 1 or k, that doesn't need to be reflected in the code. You can just overwrite the elements of x. But before you do, make sure to save the previous x, your previous iterate, because you need the old iterate and the new iterate at the same time down here to check for convergence. And the convergence test is described up here. You take the infinity norm of the difference divided by the norm of your new iterate. And you check if that is less than the tolerance. So it's a relative error that you're looking at here, a relative difference. Okay, so you check for convergence. If the error is less than the tolerance, great, you're done. So you return x, the number of iterations, and 0, indicating successful convergence. If a loop ends and you never converged, you're down here, you know it failed. So what do you return in that case? So that's how Jacobi works. Keep in mind when you are assigning vectors to other vectors, that's done by address. Make a copy if you need to. If you're getting really strange behavior, we saw that in one case, that it may be because you actually assigned an address to a vector and then accidentally overwrote something when you should have made a copy. Okay. Gauss. Now, once you have Jacobi working, Gauss-Seidel is almost identical for a full matrix. You just use this equation instead, where notice you're using entries of the old x, or the new x, and the old x. That's why you gotta have. So yeah, it's yet another reason to have both of them around. So what I'd suggest is save x into another variable first, and then update x according to this. Otherwise, it works exactly the same as Jacobi. With the sparse versions, there's a bit more involved and a bit more of a difference between the two. The idea here is, in the sparse versions, you don't have to explicitly reference an IJ entry, because not all types of sparse matrices are subscriptable, like the coordinate format or the diagonal format. You can't do that. So we're using a different form of a method. So for Jacobi, here is the matrix vector form of a method. So the matrix is split into D plus L plus U, diagonal plus strictly lower triangular part plus strictly upper triangular part. And once you have D, L, and U, then you can do this. D is a diagonal matrix. So don't actually compute the inverse or have Python compute the inverse. That is so wasteful. Instead, what you can do is use sparse functions try u and try l under scipy.sparse to extract L and U. And where this is in the documentation is, okay. So I'm looking at scipy on the main page of a documentation. I can go down here to the reference and go to Sparse Matrices. And here are all the functions for sparse matrices. And here are try L and, try L and try U that you can use to extract the upper and lower triangular parts. And there's some examples of how you use them. But MATLAB has similar functions. It pretty much behave the same way. To get the diagonal of A, use this, A dot diagonal. So then that gives you a one-dimensional array that has all the diagonal entries. So then, again, don't compute the inverse. Just divide by the diagonal entries of A in your, so you can use a loop that would do that. Okay. You're allowed to use star for matrix vector multiplication, so that makes this convenient. Like here, like for this matrix vector product right here, you can just use star, just like you could in MATLAB. So that makes things nice. Okay, so that's Jacobi. Gauss-Seidel, very similar. I have a matrix vector form here. But notice it's D plus L inverse. You're inverting a lower triangular matrix. That's forward substitution. So what you do is use this function that scipy provides. scipy.sparse.linalg.solve triangular, which by default will solve a lower triangular system. You can specify upper, but lower is what you have in this case. So use that to solve the system instead of computing an inverse. Also, if you use this function to CSR to convert D plus L to compressed sparse row format. Otherwise, if it's in some other format, your code will still work, but Python will give you a warning saying that this is inefficient. So if we're using this spsolve triangular, it recommends compressed sparse row format, but you can do this to convert. Okay. That should really just be the last thing you do. Get everything else working, at least, and producing a correct result. You'll get that annoying warning, and then you can put this conversion in to suppress it. Finally, conjugate gradient. It's a different sort of iterative method. I did not cover this in 561. Okay. So the algorithm would take way too long to explain. I think it's last time I taught 610, I spent like 3 class periods explaining it. Oops, I went too far. Okay, this is the algorithm. So I mentioned in the code, algorithm 5.2.3. Okay. Now, so fortunately, this algorithm can be implemented in a relatively straightforward way compared to the other ones. Notice there's several dot products, like you have vectors, like this vector transpose times this vector. That's a dot product. So for that, use numpy dot dot to compute the dot product of 2 vectors. Here's one matrix vector multiplication, but for that you could just use star. So this code will work whether the matrix A that's passed in is of ND array or sparse matrix, because we're using very generic operations here. Most of the operations are on vectors. Okay. Now notice here the parameter mu k as a dot product of rk with itself divided by dot product of rk minus 1 by itself. Now, this r is a residual vector that gets updated in this step. But what this means is, with this formula from you have to save the previous one. So keep track of the current and previous residuals as you go through, as this loop proceeds, so that you can compute this expression easily. Okay. Yeah, any of the parameters like initial guess, tolerance, maximum number of iterations, those are treated the same way, except for one thing. I can use a different convergence criterion. Stop iteration when the norm, infinity norm of R divided by infinity norm of B is less than the tolerance. Okay, so the residual that you're computing throughout. So use this to judge when to quit. Okay, so those are all of the functions to implement here. So I'll go ahead and post these. Okay. All right. So any questions? I know it's quite a bit, especially considering you're still dealing with the first one. Now, I've only received one submission of the first one out of 10. Well, we'll see what happens today, because I said any time today, so we'll see how it goes. Because certainly the second assignment coming up is kind of a pain too. Well, now that I think about it, it took me less time to implement the second one than the first one in the end. So, the first one was interesting. A lot of Python pitfalls that y'all are running into.
Well, though, to be fair, between running into all those pitfalls and then actually, if we saved a few MATLAB files from the previous semester,
Yeah,
it's gonna make the second one pretty straightforward.
Yeah, and actually, I think Conjugate Gradient one was the quickest of all.
Okay.
Because the other ones are looking up how to use this SciPy function or something. Didn't need to do any of that for Conjugate Gradient. Okay. Well, at this point, we have 10 minutes left. I know there's still some difficulties with our first assignment, but any questions that anyone needs to put out there now about anything?
The part in the ODE solve where you have that note that says checking the order of accuracy, you want us to do that for each method? I think it was just after the RK4 method.
Well, there's three methods that are fourth-order accurate: RK4, Adams AB4, and a predictor corrector. Yeah. So you do that for each one of those.
Okay. And we do that in the ODE solve?
Right. Yeah, because that's where you're already measuring error anyway, and you just call it twice with two different H's. Yeah.
And then the part in the ODE test at the very end where it's talking about creating those arrays, what exactly are we doing there?
An ODE test.
It says create arrays Y1, Y2, both line, compute and print the
Whoops.
editing on of the.
Oh, okay. Okay, so that's for the actual error measurement. Here we go. All right. Because Y and Y exact are lists. So if you just use array to convert, basically you're converting them into arrays.
Oh.
Yeah, and for a purpose of taking the infinity norm of a difference and getting the error and all that. Yeah, so nothing special going on there.
Okay.
Yeah.
So you said Y and Y exact are originally.
Yeah, because those are created as lists.
Okay, this.
Yeah, yeah.
And so we need to make them arrays and store them in Y1 and Y2.
Right.
Okay, and then.
Okay. All right. Any other, presumably homework 1 questions? Okay. All right. So you're still having the issue where the solution's just like a little bit off, or
And now have, so I fixed it all and put it in one.
oh, okay.
So this one here.
Right.
And then the Adams measure is working. And then the predictor is slightly off. So that's
Okay.
really
But Adam's batch 4 was working.
Mm-hmm. It's fine.
Okay.
So I'm thinking it's something just like a little bit off there.
Okay. Well, actually, let's take a look at. Okay, yeah, because predictor corrector starts off fine,
Mm-hmm.
and then. Oh, the part where it's fine
Mhm.
is where you're computing starting values using RK4.
Mhm.
So this, so the whole predictor corrector part is off. So it's because your RK4 code is correct, which is why everything's fine up to here. So here, okay, I'll bet it's probably like some sort of overriding thing, but okay. So you get your T values, Y values. Okay, call F.
That's the
Okay.
same thing I did in Adams measure.
Yep. All right. And then, okay, so you predict. Okay, so that's pass that in there, and then,
Correct.
okay.
Adams multiplier.
All right. So then you're back. Okay. Like looks good, but
That's why I say it's probably something like.
yeah. The only thing I can think of is I know why. It's the same thing as before.
So I have to save the Y.
Why? Yeah, because
So this one.
yeah.
Okay, so I save it up here.
Yes.
So Y is just equal to Y, right?
Copy.
Right. Okay, and then this one should be YN.
Yes.
And let's see.
Yeah. Oh, it's still a little bit off. Because it should be like so accurate. You can,
Like the Adam best.
yeah. Unless there's some other thing.
Yeah, you saved the copy before this step, right?
Yeah.
Mhm.
Well, actually, I'm gonna make sure about this because I haven't run predictor corrector one in a while. Because what if it's just as off?
Yeah, I figured that's what it was, that
oh.
copy thing.
No, it's on. So okay, so it's definitely supposed to work just fine. But okay, so then you update Y, pass that here. For the corrector. Okay. Okay. Oh. Wait, 9. Oh, 37, 9 over 24. Right, okay. I like free 8s. Okay. Yeah, it's so slight.
Because everything above that was the same as the Adams best for, right?
Yeah. The starting values are always exactly the same. Here, this has to be evaluated at the new t. Because it's because this corresponds to yn plus 1. Like, look at predictor corrector. Well, now the whole class can see this, so this is good. I'm still recording. All right, multi-step predictor corrector. Okay, so for example, here we compute the predict. Okay. Well, actually, here's a So here's a y tilde. Then we pass that in here. This is like your f4, tn plus 1. And what you have is effectively Tn.
So I have to do plus H.
Yes. Yeah, so sure enough, yeah, so all it would take is if the correct y is being passed, so it's ever so...
There we go.
Yep.
Okay, and then here I'm getting 3 warnings. So now I'm getting this warning where...
divide by 0, invalid value count. Ooh, that's weird. Okay, let's take a look at that. Okay, so error messages I've not seen before. Okay, so invalid value encountered in add. Okay. Most likely because of probably because of inf or an NAN.
Yeah, right here.
Oh, that would explain it. Okay, so now I can see why that's happening. All right, so that's really the fallout from other error. Okay.
Does it have to do with these 2 random dots that fall?
Probably, but it seems like something's going wrong before that. Well, also, okay, the exact solution.
It's different, right?
It's not getting all the way to.
That's what I'm saying too.
Yeah, I think the values that it's plotting are correct.
Mm-hmm.
It just never gets that far. Oh, maybe because it crashes out.
So this is essentially just like half of that.
I guess, yeah, but okay. So, all right. Yeah. So, but since it's a warning, presumably the computation continued. Okay, these are only the y values, I imagine, or are those a t value?
I think it's just T.
Oh, okay. So that's why. Yeah, all right. So, then it said, t is definitely greater than tf because it's an infinite, and that's why it stopped. Okay. But yeah, something was definitely going wrong before then. Okay, and here you've saved yn. Okay, and then, I know what you can do. Suppose this gets rejected. Y is used up here as if it's the solution beforehand, but you've already overwritten it.
Okay.
Set it back to yn if it's rejected.
So y is equal to yn dot copy.
Yeah, and I didn't do that because I use different variables for these things. Yeah. Equals.
Oh.
Okay. That's a lot of time steps, but
Yeah.
that depends on the tolerance, though.
Okay.
But the point is, it's working.
Okay.
Okay. Whew. Okay. Well, I'm actually glad I left this running because the bugs that I'm finding in people's code seem to stem from like accidentally overwriting something and then not remembering it's overwritten and then using it again, or it's data movement errors. So when you have something that's really unexplainable behavior, or very difficult to explain behavior, that's the thing to look at is, are you overwriting something that should not be overwritten because you end up needing it later? Keep in mind that arrays are passed by address. When you make an assignment, does that affect something else? And if you have an expression involving arrays, like you have an array equal to some mathematical expression involving an array, that actually behaves quite well because it already makes a copy automatically for you in that case. So then the behavior is no different than like what you see in MATLAB. It's when you do like x equals y, when x and y are arrays, where some unusual behavior can happen. You probably want to make a copy in that case. So
you have to take that into account where it says reject y. In case it doesn't reject y, you have to keep the one that you.
yeah. So there are two ways to go about this. One is if you save it in another variable before you do your computation of your Runge-Kutta stuff, then you got to restore it to that. Or if you go back to Bogacki Champagne, what I did in my solution was I have separate variables for yn plus 1, zn plus 1. I don't say y equals until I know that I'm accepting it. So it doesn't really matter either way. But yeah.
So if you, because that's the one I use, so if you use it like that, then you have to save a copy.
Right. Yeah, and then be prepared to go back to it. Yeah. And also use that. Yeah, that's what you would use. Well, actually, here you're using the updated one, but yeah, you need it down here.
Okay.
Yeah.
That's what was throwing me off right there.
Yep. Okay, and hopefully that helps Haley as well. Hi, Haley. Okay, well, now class is ending late. But it's good because it also started late. Okay, so I'll get these assignment 2 files posted, and good luck finishing assignment 1.